All right, welcome back. I think in this lecture we're going to continue with what been learning so far. Today we're going to talk about the mathematics of optimization. Okay, I'm Professor Wu. So let's get started. So the number one thing we're learning today is the notation. When you see something that looks like this, what does that mean? Or this, right? What's happening? This is asking you to find the x, okay, that you plug into this function, such that the output of the function is maximized. Okay, and this is the opposite. We're trying to find the x, right? Such when you plug into the function, such that the output of the function is minimized. So when you read this, that's what you can think of. That's what is basically asking you to do. Now, the key to optimization that you need to realize is that at an optimum point, the slope is zero, right? So if you pick, obviously, if we're trying to find a minimum point, it is right here. And if you had this point, notice that the slope, right, or the gradient is negative. That means as you increase x, you're going to decrease, right? And then over here, the slope is positive. So the only point where the slope is neither positive or negative is what we call the optimum point right here. Okay? And this optimum point means that if you know how to take the derivative, right, then if you set the derivative where derivative is basically the slope, the location for the derivative is at zero. So it's saying that why don't you just find the x such that the derivative is equal to zero? And if you do that, if you find the x that solves this problem, then you know exactly, for example, over here x is 2, right? So take this function, for example, that's right here. And if we take the derivative, right, here's the derivative. So if you take the derivative, you get this. You can pause the video, make sure you know how to find the derivative. And after that, you set the derivative to equal to zero, like this. Well, we know that x, at the x location, the derivative will be zero. Therefore, we can solve for x, which here tells us that x is equal to 2, right? Exactly the same as what we see on the graph, right? On the graph, it sees the same thing. So the conclusion is if, and that's a if, big if you can take the derivative and then solve for x when the derivative is equal to zero, then this is easy, right? This is pretty easy. Then you have the optimum solution. Okay, so that's a big if. You can't always do that, and if you can do that, we call those solutions as closed form solutions. Closed form solutions right here. So if you can do that, we have a closed form solution. If you can't, we got other problems. So let's practice. If you're in class, you can pick any four problems to solve. But obviously, if you're watching the video, you have more time. Take your time and see if you can take the derivative and solve for the x that like either maximize or minimize the function. Right. So some of them are minimization, some of them maximization, and what you can do is you can once you figure out the x, right? Let's say x is equal to 2, for example, 3, for example. And then if this is minimization, right? So minimization, and it's at 3. That means if you pick any other value like 2 or 4, right? These values should be larger, right? So if you found 3 is the minimum, you can always confirm by picking random values around it, and then it will show you that indeed 3 is. So at this point, you want to pause the video, go through each and every one of this. This will really like consolidate the idea of closed form solution when you do optimization, right? When you try to find a maximum or minimum, that's what the gradient is. Okay. All right, so I'm going to post the solution here. Here's the solution to 1, 2, 3. Here's 4 to 6. Here's 7 to 10. Okay. Also, we can solve optimization problems with Python. Over here, let's say we have this, right? And we can use Python library in SciPy, scientific Python, called minimize, if we want to minimize this. So, for example, here's the function. Notice I defined a function right here. Once I define the function, I call minimize. All right. I put the function in. This is the function I want to minimize. And I start with some initial guess for the solution, which I just guess 0. And then it will come out and solve it for you. So, so the optimal x, right? Notice how this is telling you the optimal x. So the optimal input is 3. And at the point of 3, this is the minimum value you will get out of the function, right? So this is what this Python does. Okay. Now this example is a single variate. Okay, x is a single variate. But what if we have a more complicated where x is a vector? Well, this does actually solves it as well. If you can also have a, b, right, and then you can essentially define the function. Notice how these functions are the same, and co-minimize exactly the same way. Right. In this particular case, b has two dimensions. Right. So if you do this, then it also allows you to solve the optimal input as well as the optimal value with that input, right? Ultimate output of the function. So that's the general idea. If you have a function, you're trying to find the maximum point. So like something like this, and you're trying to find the maximum GDP, for example, then you would know like what the input needs to be. All right, so if you're at home, now pause the video again, use the same idea, but except this time, use NumPy, right? Use Python to help you, and you should be able to get the solutions pretty quickly, okay? All right, now let's put everything together. I want you to, this is the question, and you essentially have a function that describes your happiness. It's a happiness equation. And your goal is to maximize your happiness depending on the input. And the input has 3 factors is like friendship, social interactions. R is like how much time you just think about your life. And S is how much you spend on academic work. So you need some kind of combination of these 3 to achieve happiness. All right. So in this particular equation. So now see if you can find all these values that you're supposed to do to maximize your happiness. Okay. The solution is here. I also have the code solution, but you would need to get the slides in order to get the code solution. Okay, so let's go move on to part 2, gradient descent. So gradient descent is a very important algorithm because it basically is the way we train neural network today. All right, so your large language models, all those things, today we use gradient descent. The problem, let me demonstrate. So far we learned that we can use the closed form solution. Right, so that means you take the derivative, set it to 0, solve for x, problem solved. Now, let me demonstrate why gradient descent is needed to solve like optimization problems. Okay, so let's say we have this right here. We're trying to find the x, and the picture here, like we can visually see what the solution is if you just plot it out. However, if you try to analytically solve it, that's a lot harder, right? If you take the derivative, it becomes here, and then that's 2x. Well, after that, how do you solve for x if we set it to 0? So let's set it to 0. And this says that, well, we have 2x is equal to e to the minus x. Can you solve for x here easily? No. No, you can't. So majority of the time, actually, you can't just easily take a function, take the derivative, and then solve for x. You for more complicated function, we really can't do that. And as a result, we still want to minimize, right? We're still trying to find a minimum point. How do we go about doing that when we cannot just take the derivative and use the closed form solution? So that's why gradient descent are needed. Okay, so that's why gradient, and we actually perform gradient descent within class. And the idea is very simple. If you pick any random point, right, at any random point, you can figure out that as you increase x, the function is going to go down or the function is going to go up, right? So if you're trying to minimize, if the function is going down, you want to keep increasing until you reach the minimum point. So by looking at the gradient, it kind of tells you whether your current location, let's say current location, should add or subtract some kind of value, right? We should put something in that kind of like incrementally pushes us towards the minimum. So let's say like you start at some low, like let's say we want to minimize this, right? So min, it's obvious that the solution's here, but let's say we can't see it. So we make a random guess. And you can kind of picture like a person. And the person is either going to walk this way or is going to walk this way, right? So x is either going to increase or decrease. That's another way to view it. And so if the person goes this way, notice that the function is going higher and higher, which is the opposite of what we want to do. So let's say that we have our current location, x now. Well, if we're trying to minimize and the derivative is positive, if the derivative is positive, we're at this current location and the derivative positive. That means if you increase x, you're going to increase the output function, but we're trying to minimize. So we don't want to increase. So if the derivative is positive, then we want to take our current location, x now, and subtract some kind of value, right? Because we want to go this way. Okay, so if the derivative is positive, we want to subtract. In contrast, if we're here, right, then what's the derivative? Well, it's going to be negative because as we increase this, the function is going down. So if the derivative is negative, then, well, if the derivative is negative, then compared to our current location, which is here, this is our current location, we want to add some value to push you this way. Okay, so this is basically the heart of how gradient descent works. Gradient, when you're trying to minimize, you want to go the opposite direction of the derivative. If the derivative is positive, you want to take a negative. If it's negative, you want to take a positive. So gradient descent is something like the current location, your current guess, minus the derivative, right? So whatever the derivative, you're going to do the minus of it, implying opposite direction. And this right here will allow you to incrementally get closer and closer and closer, right? Or does it? Well, let's give it a try. So in this particular example, if we take the derivative, we're here, we take the derivative, which is 2x. So x squared is the function, the derivative is 2x. And now if we plug our current location 2, well, our current location right now is 2, right? So this x now is 2. And then it's saying that we want to go left. We want to minus the location, right? So which makes sense. We're supposed to minus location. However, when you plug the current location in, 2 times 2, that's 4. So you get a negative 2. So you did walk towards the correct direction, but you went way too far and you ended up here. So that's not good. You don't want to go from here to here. You want to go this way. So this equation where you take the current location and update it, something is not quite right because, well, it's not quite right because, well, you're taking a step that's too big. So what we normally do is we change the step size by multiplying by a small number, which we call eta. And this eta, it could be like zero point 0.1, right? So that's like 10% of 10% of the derivative. Or you can do 0.01. So that's 1% of the derivative. And when you add these together, when you add this, for example, let's pick zero point 0.2. So you take the derivative, your current location, and you want to do the opposite of whatever derivative is, times some kind of smaller step size. And when you do this, then what happens is you end up here. So it goes from here to here, right? And then if you keep this process, it will go until you reach here. What is interesting is once you reach here, the derivative is zero, and therefore your update stops, right? Because the derivative is here. So you're going to incrementally get closer and closer to this. And then once you reach here, the derivative is basically zero, and then that's when you stop. Okay? So the idea is we just repeat this process again and then again and again, and until we reach the minimum. So over here, if you have the chance, you want to see how, like, I took a couple steps, and with the couple steps, this is what happened, right? Approaches. And this iterative algorithm, again, it is called the gradient descent. Right? This is one of the most used optimization algorithm in entire data science and machine learning. Okay? Now we can apply this to a higher dimension. So this particular question was just one dimension. But what if you're trying to minimize alpha and beta? Well, then you do it once, x now, right? And then when you take the derivative, you have the derivative with respect to alpha. So you just solve it, like depending on if you have two, you solve it twice and align them in a vector format. Okay, so this right here is how you essentially would solve this. Now, what I want you to take a piece of paper and basically see if you can obtain the next location. Okay, so if your current location is 1 and 2, what is your next location for gradient descent? Okay, pause the video. I'm going to continue. This is what you should get. And if you run the code, like if you run the code that where you, like over here is the function, right? So this is the function. And then I wrote the derivative function somewhere. Yes. So the derivative function is right here. And basically, if I run it in a loop where your current location keep subtracting the step size times the derivative. If you just keep doing that, you will reach the minimum. And you can see that the function output, if I plot it out, looks like this, right? So you're trying to meet, so the function keeps getting lower and lower and lower. Right? So when you have the chance, also study the code that does this. So you get the idea of how a function is minimized. All right, so let's practice this idea. All right, see, here is the function you want to minimize. Now you want to pause the video and make sure you can do this. Okay. Here's the solution. Ooh, here we go. And over here is the code solution. Like you want to take the chance, you want to see if you can achieve this. Now, when we take the derivative of this, right, we learn the derivative. The derivative looks something like this. So this was actually, I believe, on your exam. So if you know how to take the derivative, you can just like use this as a derivative for your code. However, it turns out that if you follow through a sequence of derivations, instead of having your derivative in terms of like vectors, we can combine the operations together such that we don't need a sum anymore. And this right here, if you follow the derivation, is the result. So notice how over here we're going x1, x2, x3, whereas capital X here is the entire matrix where each row Each row is a single vector. And this right here is how you normally would want to use as a derivative. Okay. Over here is another one. This is the objective function. And basically, it just says that the objective function can be written this way. And this derivation, you can read it yourself when you have the chance. In a more advanced class, I will make you prove it. But here, you just need to be aware that you can convert this like summation into a more compact form, and it's easier to code. So this is easy for Python, like, whereas it's harder to code this slightly. All right, your last question. Pause the video. Make sure you go through this and understand these concepts. And that's basically it for today. That's it. Good luck.